reactive hit me several years ago when I was running a program at a nuclear power plant back in the US. And I walked into the maintenance superintendent's office and I said, hey, look, I've got all this data, we got a bad bearing on this motor, we got to shut it down, we got to change it, let's save this machine. And he looked at me and he says, you've got to stop talking like that. He says, you always say you've saved this machine. And he said, from my perspective, you haven't saved anything. And I'm curious to know, and oh, by the way, I love presenting, but I hate lecturing. So let's make this, nice and interactive. I'm happy to take questions or comments at any point while I'm up here. But I'm curious to know, how many of us in the room have been told the same thing by the maintenance superintendent or the director that, you really haven't done anything for me because by identifying the fact that I've got to change this bearing or we have a problem on a bearing, all you've done is created more work for me. Anybody? I mean, come on, it can't just be two of us, three. I know, the rest of you guys just don't want to admit to it. I kind of know how that goes. And so I started thinking in terms of, what are we really trying to do? We go out, we say, we talk about the, reactive maintenance, oh, that's a bad thing. Run to failure, we don't like that. We could do preventive maintenance where we're basically rebuilding the machine over time, but we really need to do this predictive maintenance thing. And we need to let the machine tell us when it's time to take action. And when we do that, though, aren't we really kind of using technology to take us into a reactive mode? When you really think about it. We're saying, hey, I took data on this machine, I took vibration data, and the vibration data is telling me that I've got a bad bearing. So now I need to react to the fact that there's a bad bearing and change it. Maybe if we changed how we think about things, we might be able to get a little more proactive and get in front of some of these kinds of problems. And from that perspective, I'm willing to bet everybody in this room already owns every piece of technology that you need in order to move in that direction. Excuse me. So if I can figure this out, let's talk about moving from predictive, which is kind of the leading edge of reactive, into proactive, and see if we can get people like maintenance superintendents and directors to stand up next to us and say, yeah, we really did save that machine, as opposed to, you made me spend money and resources to replace a bearing that, at the end of the day, when it fails, I was going to have to replace it anyway. So what I like to do is, I've kind of got my own definition of reliability. And from my perspective, a machine has achieved its reliability goals if it can provide you with all of the following three attributes. It has to be able to produce whatever product it is you're making reliably, effectively, cost-effectively, safely, but it needs to be able to produce with three primary attributes. And those attributes would be, it needs to be able to produce where should I be pointing this?
It doesn't need to, it's radio.
Oh, okay.
All right.
It needs to be able to produce on demand, at capacity, and within quality standards. That's it. If you're not able to produce when you throw the switch, if you're not able to produce at full capacity, and if you're not able to produce parts that meet the output quality standards, then I maintain that machine has in fact functionally failed. So when we talk about functional failure, I'm not always talking about, the things come crashing down, the bearings have all crumbled, the shaft is tearing itself apart and there's bits of metal flying around the room. Basically, if you can't produce on demand or at capacity or within quality standards, then you have in fact functionally failed, even though the machine may still be running. Everybody good with that? Cool. If we're going to be successful with technology-based condition monitoring and evaluation, and I know you weren't expecting a quiz this early in the morning, but what is the most important aspect in your mind for conducting successful condition monitoring and evaluation? Anybody, want to throw anything out there?
P to F?
The P to F curve. Did you look at my notes? the P to F curve as a representation of what's going on, I think is an extremely important thing for people to understand. And I know Jason talked a little bit about it yesterday. We're going to go into a little more depth with the PF curve and some things that I kind of felt were missing. And we're going to move forward with that. But anybody else have anything to throw out there? Well, that's okay. I usually get all sorts of good answers from folks, you know, anything from, you know, you've got to have a level 3 certified vibration analyst on staff, or you need to use this technology or that technology or the other technology. From my perspective, though, I think the single most important thing to know and understand in order to have a successful condition monitoring and evaluation program is a thorough understanding of your machinery. In 3 terms. Basically, how it's built, how it's put together, and how it's supposed to run. Because if you understand these at the gut level of a machine, then chances are pretty good you already know how it's likely to fail in service. I mean, it sounds corny to say it, but the most successful programs are run by people who can walk up to a machine and look at it as though they had Superman's X-ray vision, and just be standing there looking at the machine, but visualizing what's going on inside. If you've got that level of understanding of the machinery, then you know the technology that you apply is a relatively simple leap forward. So when we understand the machine and we know how they're likely to become damaged or how they're likely to fail in service, which I can pretty well guarantee you everybody in this room already knows this and can already do it. We apply that, we know how it's likely to be damaged, we know how quickly it's likely to progress from when the damage starts to when it fails. We understand the root cause failure mechanisms that are in play that cause the problems on the machinery. And ultimately, we know or we have an understanding of how these issues manifest themselves. I mean, that's really what condition monitoring, successful condition monitoring, and evaluation for reliability improvement is all about. So when we understand, you know, all of these factors, we know what condition monitoring and evaluation technology to apply and how frequently we need to apply it. So the comment on the PF curve, as Jason indicated yesterday, Mowbray in the late 90s, as far as I can tell, is the first one that ever actually published it. But basically, when we start, we're looking at the time health of a machine. And when we start, we're looking from when a machine is first repaired, rebuilt, brand new, put into service. In theory, it's going to run with good functional health for some period of time. It gets to a point where damage starts. And when I talk about damage on the machine, I'm talking about an irreversible damage. Something physically bad has taken place. Once that bad thing has happened, the operating health of that machine will start to degrade. I mean, it's not going to fix itself. The problem, when you've got physical damage, the problem is just not ever going to go away on its own until it gets to the point of functional failure. And again, for me, functional failure doesn't necessarily mean bits of metal flying around the room because the thing's gone catastrophic. It just means that machine is no longer able to produce on demand, at capacity, or within quality standards. Any one of those 3 attributes is no longer achievable, that machine's functionally failed, in my opinion. What Mowbray said, and again, as Jason mentioned yesterday, is somewhere along that degradation curve, he introduced it as a point P. The point P represents the time where the potential for failure is recognized. It can be identified by some objective measurement or observation. So you've got degradation, it's progressing, and then it gets to the point where you can see it. Using some technology, you know, it could be, you know, you could hear it, it could be just a, you know, a visual observation. But the bottom line is we now recognize that there's a problem. So the time from point P, where you can first perceive the fact that failure is in your future, until we get to the functional failure itself, Mowbray refers to that as the PF interval. And basically, we in the condition monitoring and evaluation on the supplier side of the business for a lot of years have been using that PF interval to justify what type of technology and how we apply the technology to help folks recognize that they've got a problem at an early enough opportunity to plan to take some level of corrective action prior to the functional failure. I mean, that's really been, whether a lot of us have admitted it or not over the years, it's really been the basis for how we say to someone, I recommend that you do this, or I recommend you do that. It's based on understanding the machine, how it's built, put together, and supposed to run, the failure mechanisms, and how those failure mechanisms manifest themselves. But we've always been on that right-hand side of the curve. So we've put ourselves over the years, and we've done this, as a vibration community, we've always put ourselves on the right-hand side of the damage point. When we identify, that something's gone bad, it's not a question of if, it becomes a question of when. One other thing that we tend to ignore or not pay enough attention to, in my opinion, is the fact that machines have multiple failure mechanisms. And everybody's seen the version of the PF curve where somebody's going to say, well, you've got the P1 point, and that's the closest one to where the damage happens, and this technology sees it first, and then that technology, and on and on and on until you get down the line. I really don't want to go there specifically. But the point is, different technologies will see different failure mechanisms in play at different times along that progression from good functional health down to functional failure. But the other thing that we need to keep in mind is that there's multiple failure modes. And I'm only going to just show 3 as an example. But machines have multiple failure modes, and each of those multiple failure modes have different point Ps along their failure progression, depending upon what technology you use to identify. And obviously, with vibration over the years, we've been pretty proud of the fact that vibration is one of the technologies that allows us to identify the fact and recognize the fact that damage has happened very early in the process, after the actual irreversible damage has started. Everybody good with this so far? I like to see the heads doing this. That's helpful. So when we take the PF curve to the next level, we can look at it in terms of a practical application from what we've called for a long time the cost and consequences curve. The x-axis of this is kind of the inverse of time. It's how quickly something goes from initial indication of a problem to functional failure on the horizontal axis, in the range of problems that take years to develop and get to the point where things don't run reliably anymore, all the way down to the rapid onset failure that can literally happen in a matter of seconds. On the vertical axis, we talk about the cost consequences. And when I think in terms of cost consequences, I don't think in terms of just what the mechanical maintenance superintendent cares about, which is his budget, the cost of the parts to do the repair work, or the cost to him in terms of manpower and resources. I'm also including things like the cost of lost productivity. There was a nuclear power plant in the U.S. that I'm familiar with, but I'm not allowed to say which one it was, other than it wasn't the one that I worked at. But a good friend of mine who was in a similar role in a different facility went through this experience, and it was not particularly pleasant for him. There was a real rinky-dink pump that was surprisingly critical to the process. Through vibration, he recognized that the bearings, it was an overhung configuration, the bearings were degrading. He could see that in the vibration. The lube oil guy on site went out and was drawing samples, and he was getting bits of metal in the lubricant. I mean, this pump was maybe this big, 75 horsepower, but it was part of the process where, even though it was this rinky-dink little pump, it was extremely critical. You could not run that reactor at full power without this pump maintaining the reactor chemistry levels. So the vibe guy and the lube oil guy all went to the plant manager and said, we got a serious problem. They came up with a plan where they were gonna bring the plant down to 90% over the course of a weekend. It was also a nasty, high radiation, high contamination, icky, no people want to be in here kind of environment. They're going to bring the plant down to 90% over the weekend, have all the materials staged, do all the proper planning, go in, do the replacement, and they would be able to have the plant back up to 100% power by the time, they needed to be base load, full power on Monday morning for when industry restarted. Plant management decided that they didn't want to take that kind of a downpower. And the plant manager, because you got to know everything to be a plant manager, because that's what it takes, at least in the nuclear industry in the U.S. You know everything, nobody else knows anything. Plant manager says, we don't believe anything bad's going to happen. It's going to continue to run. It'll run just fine. They were looking at an outage, 4 or 5 months down the road. So when the plant manager said to my friend, I don't even want to know about this problem anymore. I'm telling you, we're not going to take any action. 2.5 weeks later on a Tuesday afternoon, that pump failed. There were bits of metal flying around the room. Nasty contaminated water going all over the place. They did a really good job of reacting to it from a get the plant back into a safe condition level. Unfortunately, they had to come crashing down. They had to pay expediting fees. They had to pay overtime. They weren't prepared. They didn't have a spare pump on the shelf in the stock room. And they were looking at what at the time, and this was the mid-1990s, from a, what's it costing us to do this repair and replacement? It was about if I remember right, about a $60,000 price tag. The question though is, what was the most critical aspect for them financially? This power plant was down for 7 days. $60,000 to do all of the activities associated with the repair and the replacement really could be considered chump change when you recognize the fact that being down for a week, there was $12.7 million worth of lost revenue. All because one guy didn't want to buy into the confirming indication of both vibration and lube oil, telling him that he had irreversible damage that was progressing and they needed to do some responsible action, take some responsible action in order to correct it. And so when I heard that story from my colleague, it really hit home for me the fact that the vertical axis on this really does need to be cost consequences. What are the risks? What is the cost associated with either doing something or not doing something? So when we look at this, for those things, and I'm not going to, again, I'm not referring to any specific technology, but for those things that degrade gradually, they take a long period of time to go from initial indication of a problem to the functional failure on that machine. We can probably be looking at things like walk-around portable-based systems. They could be portable vibration data collectors, could be portable infrared thermography. Again, I'm trying to be not particularly technology specific here, but if the cost consequences of the failure and this is potentially an either-or situation, if the cost consequences or the amount of time from initial indication to failure aren't really that great, go ahead and use portable instruments. There we go. On the other hand, as you start moving up the value chain in terms of the cost consequences or your ability financially to tolerate a sudden unexpected failure of the machine increases, or the time from first indication to functional failure starts to move from years and months down into months to weeks to maybe even some number of days, we ought to be looking at some installed technology that is periodically evaluating the machine, taking data, giving you an evaluation of the machine's condition. Again, all with the idea of saying, I need to know as early as possible in the process so that I can do the right planning, scheduling, get the resources in place so we don't have that, that huge cost, which, like I said, more often than not is really lost productivity more than the cost to do the repair. And similarly, if we've got machines that can fail quite rapidly, in a very short period of time, or they may be of extremely high cost consequence when they go down, we probably need to be looking at continuous online monitoring. Again, we're not going to talk specific technology, but all of the technologies can be thought of using this same approach. And this is one of the things, again, as a technologist, we've been using kind of this interpretation or this adaptation of the PF curve to help our clients justify, do I just want to use a portable walk-around device, or do I actually want to go all the way up to a machine or an instrument that's monitoring on a full-time basis to get to shut down, protection and control. So we good with this? Cool, because now we're going to go back to the PF curve. And like Turner Classic Movies in the States has taken all the old movies and colorized them, I kind of felt that the PF curve needed just a little bit more jazz when we look at it. So again, when we talk predictive stuff, we're talking the right-hand side of the curve. Once the damage itself is actually started, it progresses to the point where our instruments or our senses can detect the fact that something's gone wrong, and if we don't address it, damage will eventually get to the point where we get to that poofy little cloud at the end, functional failure, not able to produce on demand at capacity or within quality standards. What I think we need to do a better job of as a reliability community is working before the damage actually starts. And so what I've done is I've added this little green to blue transition zone to the left side of the curve before we get to the point where the damage starts. I was talking with Jason last night. I think Jason kind of mentioned a little bit about the flat part of the curve. But my position is that if we started to focus ourselves not on indications of damage, I mean, we can never stop doing that. Don't make it sound like I'm not in favor of looking for known bad bearings and things like that. But if we would spend just a little bit more time focusing on the manifestations or the indications of root cause failure mechanisms, we could do ourselves a lot of good. We could walk up to that maintenance superintendent and say, I'm seeing a problem over here. It hasn't done damage yet, but perhaps we need to do something over here, and we can prevent damage from starting. Now you're talking to him like you're his partner, and you're going to help him not expend his resources, while at the same time ensuring the continuing operating life or the longevity of the machine itself. So at this point, if I could go up to the maintenance manager and say, we need to do this little tweak here or do something over there, because if we don't, we're going to hit the damage point. And then I'm going to be coming back to you and saying, hey, you got to change this out, you got to change this bearing, or whatever the appropriate corrective action is. If we can focus to the left, we really do ourselves a huge, huge service. And in some of the case studies, things that I've been involved with directly, and case studies that I've gotten from colleagues and other friends on the reliability side of the business, I'm going to propose to you that there's another point P on this curve. And I'm going to call that the proactive point P. When you go through this green to blue transition zone that I've got up on the screen, where everything's good, we're humming along, there's no damage, there's no indication of a problem, but all of a sudden we get to a point where some damage-causing condition, some root cause failure mechanism is in play. From my perspective, as a community, or a reliability community, even more than just a vibration community, because let's face it, vibration is a technique to help enhance overall reliability. We owe it to ourselves, to the people that we work for, to try and help them avoid getting to the damage part. So if you can identify the fact that a root cause failure mechanism is in play and address the root cause failure mechanism before the damage starts, then we're really talking about things on a literally on a proactive basis. So I kind of segment this a little bit, And these methods on the right are the methods that we use to identify the fact that there is damage that has started and is progressing. But if we focused on the left and started thinking in terms of, I need to identify the fact that there is a root cause failure mechanism that is actually in play. And if I can address that root cause failure mechanism, I can avoid getting to the damage point. We can save ourselves, a significant amount of money in terms of not having to do the big job in favor of simply doing the little job. Because the one thing that I think most people in this room will probably agree with, functional failure on a machine is not an event. It's an event if you don't recognize it in advance. It's a process. Machines generally, bearings don't just fail out of the blue. Machines don't just fly apart. There's something that causes that to happen. So that what we found over the years from, again, personal experience and conversations and case histories I've gotten from colleagues, not only in industries that I've personally worked in, but other industries, it's pretty easy to see that if you can address the problem at the root cause level before the damage starts and prevent the damage from happening, you never get to that point in the middle where it goes from blue to yellow. But when you do get to that point, clearly you've got a step change in the cost to repair or return to service. And again, the potential exists for the increased cost associated with lost productivity when you get to that point. And of course, if it continues to progress unaddressed, as time goes on, it only becomes more and more costly in terms of parts, repair, labor, but even more importantly, lost productivity. If you ignore it, it just gets worse over time. Is that consistent with you guys' experience? Anybody got any questions, comments, concerns? I'll even take opposing viewpoints. Go ahead.
I think it's important to realise that Mowbray, although he came up with this years ago, in his book he spends about the first 4 or 5 chapters explaining how this came about. And one of the things is, on the, where you've got proactive there, that's in their case talking about a widget that's installed to a specification.
Right.
And that's where the issue comes in with looking at that curve and not understanding that. In other words, the failure mode is the same regardless. And as you quite rightly showed there, those actual modes, or the steepness of it, the sudden failure type thing, is as much to do with the installation specification as the actual plant.
Well, that's a good point. I mean, basically what we're saying, and I agree, Mowbray starts from the point that the machine's in good condition when it starts, it's installed properly, it's installed to specification, clearances are what they need to be, you've got the right lubricant in there, you're running it in accordance with the manufacturer's recommendations, and then over time, things start going bad. And obviously, we want to focus on, keeping those bad things under control and recognizing when they've started. Yes, sir.
Over the years, I've been appreciated that we've got to be more into the blue zone.
Mm-hmm.
And I've been doing VA for close on 40 years. And over the years, I've mentioned that we're operating in that situations like pump cavitation. It's a simple one, a common one. But when you look at the cost to repair the fault, which is a design problem, because of the way they've got their pipework set up, it's freaking horrendous. They'd rather run, just as we do now, just run until we get to that P point and then I'll monitor and try and predict. And generally reasonably well, we're getting close to the point when have it appropriately cleaned. But convincing people that there is a problem that we are in that blue zone is quite difficult. And sometimes it's a simple fix and that's fine, but often it's a very expensive fix. And they've got to let it go. And I've been proved wrong quite a few times. It's sad to say, saying this thing's not good. It's going to fall over soon because it's running so rough. And it keeps on going for years and years.
Well, I think we've all had that happen. You know, you see the indication of just, and I'm for the SKF and the FAEG guys who are here, I don't mean to just pick on bearings in general, but I'm going to pick on bearings. It's what I do. But, you know, how many times over the years have we as practitioners gone out, taken data on a machine and said, oh man, this bearing's in a serious state of distress. Mechanics go out, they pull the machine out of service, they take it apart, they take the old bearings out, they put the new bearings in, they wipe all the grease off the old bearings, and they say, I don't see anything wrong here. I mean, come on, let's go, confess. Come on, guys. There are not enough hands up in here. But you know, when we talk about it, there's a lot of stuff, you know, going on in bearings that you can't see on the surface. You know, it's the subsurface cracking that develops that you can pick up with your instrumentation. And when you choose to react to it, it's up to you, it's up to the scheduling, it's up to the plant requirements. You know, I've talked for a long time about, you know, what it is we really do when we go out and take vibration data on a machine. And again, you know, we like to say, hey, you know, we're the guys with the pointy hats with the stars and the half moons. We are the wizards. We go out there and we say, hey, you know, I can tell you, you know, what's good, what's bad, what's indifferent about this particular machine. But, you know, at the end of the day, what are we really providing our management with? It's a planning tool. It's a very high technology, you know, very knowledge, you know, very tech-intensive planning device. It's rare, especially if you're doing like a portable walk-around program. Think about it. It's rare to walk up to a machine, take data on it, and see that it's in such a serious state of distress that it's like, oh my God, I've got to take this out of service right now and, you know, address this immediately. How many times does that happen over the years? Not very many. I mean, well, yeah, you're right. It's screaming at you. You know, you got to do this before you even walk up to it. We had a couple of those over the years, but really not all that many that, you know, you do like your walk around monthly or, you know, bi-weekly or whatever, that you're lucky enough to say, oh wow, I caught this, I just saved this machine. And, you know, like I said at the beginning, the maintenance superintendent says, you didn't save me anything. You just made me do more work. But when you think about it, it's a planning tool. And when I go back to my friend's example from his nuclear plant, he gave them all the information that they needed in order to properly plan to, you know, reduce power, deal with those consequences, go through all of the, you know, the practice work that they had to do because, you know, in a high radiation, high contamination environment, you don't want to be walking in there and seeing something for the very first time. You know, they had a pretty good program set up so that when it actually came time to reduce power and send the guys in there into the high rad environment that nobody wants to be in for any period of time, they tried to put themselves in the best position to, you know, plan the work right, have all the parts available, do it expeditiously, get in and out as quickly and safely and effectively as they could. They presented the plan to management, and management said, yeah, we're not going to do that. But really, when you think about it, that's what we do. Hopefully, we're providing our management team with enough information to appropriately plan and schedule the work. And, you know, if we can do that and if we can be successful with that, things are good. So moving on from here, as I said, I propose to you that there is a proactive point P where you can identify the fact that a root cause failure mechanism or multiple failure mechanisms is in play. When I think back historically over the years, I always used to have a friendly rivalry with the lube oil guys. Because the lube oil guys, for years and years and years, always felt that they had the lock on proactive condition monitoring technology. I mean, how many of us have heard that? We've all heard that. You know, the lube oil guys will stand up there and say, lube oil monitoring is going to give you really proactive stuff because we can identify things in the lube oil that are going to cause a problem for the bearing. Chris, if I made a statement that greater than 50% of failed bearings failed because of some issue with the lubrication, how accurate, as a bearing guy, would you say that is?
Oh, yeah.
You're my hero. I've seen a number of studies. I just needed to get validation from a bearing supplier. I've seen a number of different studies over the years from various different bearing manufacturers. And what they do is when they get bearings back for failure analysis and they take a good hard look at them, it's really rare to find a bearing that is metallurgically or from a manufacturing perspective has failed. What kills more bearings than anything else is problems associated with the lubrication. You know, because it's the lubricant that really carries the load, right? Separates, you know, the metal parts from actually making, you know, direct contact with each other. When that lubricant degrades and can no longer carry the load, you're going to run into issues. And it's the lube oil guys who have always said, you know, I can go proactive because I can see that there's moisture in the oil. Or I can see that there's, you know, solid silicate particulate, which if you don't get that out of the oil is just going to chew up the surfaces and degrade the bearing. Or I can tell, you know, when the additives are depleted and it's not carrying the load anymore, or if the viscosity is wrong, or, you know, on and on and on. And for years, they're the ones that have been saying, we're proactive, you guys with vibration are reactive. And I couldn't disagree with that more from a personal perspective. I can pretty well guarantee you that everybody in this room has the capability in their vibration systems to be able to look at the data that you're acquiring and recognize when there's a problem with the lubricant. We can see it. Now, it would be ridiculous for me to stand up here and say, I can tell you the difference between moisture in the oil or contaminants or, you know, just silicates or dirt. We can't do that with vibration techniques. But we can look at the thing and say, this lubricant is not doing its job. And if it's not doing its job, you know, you can always draw a sample to figure out why. But if we can tell you with a vibration mechanism, or with a vibration method, that the lubricant's not doing its job, with any luck, we can start, you know, getting some corrective action in place, moving in the right direction to get people to address the problem with the lubricant. Like I said, I can't tell you what it is, but I can tell you that it exists and that it's in play. And, you know, as much as I'd like to stand up here and say, hey, you know, our vibration stuff has the best detection method, I'd like to be able to say that, but, you know, face it, all of our competitors have some, you know, pretty darn good methods for identifying and recognizing these kinds of problems in machines. And so if you're not using that, and if you're not looking at using these techniques proactively to say, hey, this failure mechanism is in play, don't know, may not know exactly what it is. And honestly, I don't care. Just knowing is enough for me to move forward. The other thing that, and I'll be talking a little bit more about this in my presentation tomorrow, but the other thing that I'm really big on focusing on is changes from normal operating behavior on a machine. But that's kind of like, consider this the teaser before the commercial for tomorrow's conversation. But if I can conclude, you know, the discussion of proactively looking at your data rather than just looking for, you know, the classic bearing defect frequencies and their harmonics. Because face it, we all know when you see those classic frequencies, it's already too late. It's not a question of if, it's a question of when. I like to talk about one of the primary root cause failure mechanisms in machinery, and that's friction. Pure and simple, it's friction. Localized excessive heat buildup, is what's going to lead to more functional failures than just about anything else. So when we talk about friction as a primary root cause, there's different things that affect friction. Friction could be affected operationally. Speed, load, temperatures, pressures, what you happen to be doing with the machine at any given time impacts the friction that the rolling elements or the journals or whatever, the most sensitive parts of the machine are likely to undergo. Similarly, the lubricant condition, as we've been discussing, impacts the friction. If the lubricant's not able to carry the load, heat's going to increase, heat's going to build up, it's going to increase, it's going to lead to failures. And surface condition also affects friction. But generally speaking, unless contamination, particulate contamination is in play, or a lubricant is really degraded, it's rare these days, at least in my experience. I'm sure others may have different experiences here in the room, but I think it's rare to find initial surface conditions in bearings being a problem. The bottom line is, when we talk about what's going on with damage, friction leads to damage, and friction, I think of friction as impacts at the microscopic level. Because face it, you never get a perfectly smooth surface. We like to think we will, but we don't always get there. Friction is impacts at the micro level. Damage is impacts at the macro level. Right? I mean, everybody can all pretty much agree to that. So that if we can recognize the increases in friction before we actually get to the point where we're seeing the impacts, which are the indication of damage, then we've done our job. And again, we've taken our program from a reactive damage assessment program to a predictive, to a proactive, I can get this solved before the bad thing happens approach. Then I really think we're doing ourselves, our technology, our whole industry a major service. And ultimately, unaddressed friction leads to damage. And just from my experience over the years dealing with a ton of folks, I really don't think we do as much as we can with our vibration monitoring to focus on friction as a failure mechanism. And like I said, I think we all pretty much already have what it takes in order to do that. Now I know this is a copyrighted document, but I didn't think I'd get in too much trouble for copying it and displaying it to you. This is a paper that was presented at this conference back in, I believe it was 2006. It talks about ultimately the techniques that you can use for identifying bearing damage, gear damage, things like that. But these techniques, these high-frequency demodulation methods, all work for identifying friction. And rather than go through this, and I promise I'm not going to read this to you, you can find it in the VANZ archives. I'm sure this is available online still. Yeah. If anybody who's not familiar with these methods, I really strongly encourage you to look through this document. It's a document that I've used as a reference many, many times over. But when we talk about friction as a root cause failure, I would like to go over this just for a moment. Because when we're using our acceleration envelope demodulation, peak view, spike energy, demod, G's enveloping, I don't care what you call it, they're all essentially the same. They're not identical, but they do the same job. I strongly, strongly encourage you to be using these techniques and look for some of these subtle indications, these subtle changes. Because an increase in friction, which is what's going to lead to damage in most cases, there's all sorts of different ways that you can see it. And the actions that you as the analyst or the person making the recommendation to management as to what needs to be done can start doing. And again, I'm not going to read this to you. It's available. The presentation's available on the website so that you can take this and look at it in more detail at your leisure. But basically, when you start to see the increase in friction, it's time to look for what's easy. The operational changes, change in speed, change in load, change in valve position. I mean, how many times do we go out in the field reacting when somebody says, hey, this machine sounds funny. You need to come out here with your analyzer and figure out what's going on. What's the first question that you normally ask when you get out to the machine? Maybe even before you've turned the power on your data collector or attached the accelerometer to the first bearing. What's the first question you ask?
What's changed? What have you done?
What have you done? I'm serious. I'm absolutely serious. When I was at the power plant, I used to get calls all the time. Bob, you got to come on. You got to check this out. You got to listen to it. It got to the point where after I'd been there a few months, I would go out there. I would leave my data collector at my desk. I would just go out and take a listen to it. And I actually said to this one guy, we walked out to this machine and it sounded really, really nasty. And he says, geez, you came out here, but you didn't even bring your collector. Why not? And I listened to it for about 3 seconds. And I said, all right, here's what I want you to do. I want you to close your eyes. I want you to put your hands out in front of you and make 2 fists with your fists oriented up and down. You're in your car. You're driving down the road and you hear the exact same noise. What do you think the problem is? Do I really need to get my analyzer out here? Alternator bearing, this, that, or the other thing. One of my kids, when he went off to university, didn't live too far from home, but we wanted him to have the, away at college experience. He came home about every other weekend. One day he came home, he walks in and he says, hey Dad, he said, something's wrong with my car, you got to listen to it. Okay, we fire it up. The alternator bearings were just screaming. I said, shut it down, shut it down. I said, how long has it been sounding like this? Oh, I don't know, maybe the last couple of months. I said, why are we just talking about this now? He says, well, I'd be driving down the road and I'd be hearing it, and I'd just crank up the volume on the stereo. He says, it got to the point where I can't crank the volume up any louder. So I figured I'd better ask you. But realistically, when we go out in the field, we talk to people who are listening to things that sound funny. The first question I always ask is, what's different today? What have we done differently? Do we have 3 pumps and we put 2 in service? Have we monkeyed with the valve lineups? There's a client of mine several years ago who was using the high frequency, the demodulation techniques religiously on his machinery. And they had a sealed, sealless pump, canned motor pump. Everybody's familiar with those, right? The kind of pumps that move, really caustic, nasty, icky stuff, and you don't want seals, interfaces, bearings. The bearings are typically lubricated by the process fluid. So any perturbation in the process fluid flow results in a bad change to lubricant flow to the bearing. They were going along and everything was fine. They shut down and did some maintenance, didn't touch this pump or anything anywhere near the pump. Brought the plant back online, and the analyst noticed a really slow, gradual increase in the high-frequency demodulated values. There was no spectral content, but just an increase. It just kept going up and up and up and up and up, until eventually it got to the point where he did have spectral content, indicative of pending bearing failure. So it got a little bit worse. They finally, they shut it down. They took it out and they put a whole new pump in place. Brand new, spec'd out good, pre-maintenance, everything. They put it in service, and when they started it, the levels were higher at the get-go. But they didn't think too much about it. Maybe we'll let the bearings wear in for a couple of days. But the bearings didn't seem to wear in. It just kept starting to work its way up and up and up and up and up. So they're scratching their heads. They called us in, we started looking not just at the pump itself, but we started looking at what was going on in the rest of the process. And the question I have for you is, what happened? They took this part of the process out of service before it got to the point where, you know, they had damaged the bearing. We did a pretty extensive evaluation of the operating parameters, which, again, I'm hugely in favor of focusing on operating parameters when you start to see a change. Because if you can explain a change with an operating parameter, you might be able to tweak it back down and, you know, get things going the way they should again. What ended up happening was when they had done their maintenance activities in the plant, they were doing some stuff way downstream. When they brought the plant back online, they weren't getting exactly the output that they were hoping for, but it was within an acceptable range. So as long as it was in the acceptable range, they didn't really care about the fact that they weren't getting 100%, because they didn't really need to do 100% at that particular point in time. What we were able to determine, though, was with the maintenance activities completed, there was a mispositioned valve that was ultimately restricting the flow that was coming out of this pump. So this pump was trying to work harder than it should have been working, basically driving the impeller into the thrust bearing, which, because of the reduced flow, was not getting sufficient lubrication. And basically, it was an operational issue that was killing this machine. From a proactive perspective, looking at those operating parameters and recognizing the changes from normal operation, finally figured out what was going on when they realized, oh, damn, you know, this valve needs to be open farther. You know, they opened the valve, started the line back up, levels went right down where they belong, and life was good. So, you know, asking the question of what's different really goes a long way to figuring out what's going on. But they never even would have known that that valve was significantly out of position had it not been for the indication on this one particular machine. And so then they realized, geez, we killed this original machine ourselves. And they really, you know, recognize that it's time to start focusing on, you know, more and more on the demodulation methods that recognize when there's a change in friction, and focus on that change in friction so that you can catch it as early as possible. And I like to think of it in terms of when you get the initial increase in friction, you start looking. If you can't justify it operationally, look at the lubricant. If the lubricant, you know, ought to probably show you that there's something going on. If it continues, you start to see starting to see damage, you'll probably see a step change in that overall demodulated value. And eventually, it's going to continue. You're going to start to see it in the acceleration spectrum. I mean, nothing makes me crazier than somebody saying to me, but Bob, I didn't see the defect frequencies in the velocity spectrum. From my perspective, when you start seeing the defect frequencies in the velocity spectrum, it's time to run and hide. And I think, you know, most of us can agree that when it gets to that point where the velocity data shows the bearing problem, you've missed something, you know, a long time ago in the process. Everybody okay with that? Again, I'm not going to read it to you. You've got copies of it with the program. So basically, that's kind of what I wanted to leave everybody with. You know, in summary, I think we as a community owe it to ourselves to do a more proactive job. Focus on the proactive indications. Focus on the proactive indications with technology that we probably already own. And I guarantee you that if you don't own the right piece of technology to let you see these proactive indications, there's a whole bunch of folks in that room right across that wall that would be more than happy to discuss it with you. So with that in mind, I'm going to say reactive bad, proactive good, or predictive good. Proactive is best. Anybody have any questions, comments, issues, concerns?
Yeah, I just, you know, it's an interesting point to take to, or one really consider taking that predictive curve even further into the past. And prior, even in the design phase, the too much price-driven selection, for example, of a pump that really is
Right.
doomed to failure from the day it goes in. And you know, this is something that can also, I believe, be considered in the when it comes to replacing parts or specifying them in the first instance. You know, I think it's going back even further to some extent. You know.
Well, I think you're absolutely right about that. Engineering changes are always the hardest changes to make to improve the performance, reliability and longevity of a system. And unfortunately, we've seen what I consider to be a really nasty trend over the last 10 to 15 years of the corporate requirement to make sure the numbers are good this month and next month and the month after that. And there's a lot less long-term thinking that's going on. And so when I look at it from the perspective of what are the things that I can either control or at least influence, I want to try and focus on those things that I can influence that give us the best opportunity to not get into the point where failure becomes imminent and damage happens. And unfortunately, most companies, their appetite these days for shutting down and making significant engineering changes, as you were alluding to also, fewer and fewer companies are having much of an appetite for that at all. And it's basically because they have to make their numbers this month, they have to make their numbers next month, and oh my God, I do not want to take that kind of a financial hit because I got to return value to the shareholders, and they don't really care what I'm thinking about for the future. They really only care what their dividend or their stock price look like today. Yes, sir.
So the most proactive thing you can do is drown your account.
Right along with shooting your lawyers. I think my time is up. Thanks.